Okay, welcome to our second to last lecture. And I would like to thank our diehards who are still here right towards the end, even with everything coming due and springtime out in the air and everything. So I do appreciate it. We're almost to the end of the semester, and we have only a couple things left to cover. Today we're going to cover analysis of variance, which is an introduction to one of the most practical and useful statistical methods that we have. This is just a little toe in the water of analysis of variance. It is a course on which a topic on which entire courses are taught in statistics programs, and it's been said that most of statistics can in one way or another be boiled down to analysis of variance. So this is just going to be a little teaser, but still enough to be quite useful for a number of things. And the principles that we covered today can be will be useful to you even as you look at published papers of more complex analysis of variance. You'll know what they're talking about. So we're going to cover just one-way analysis of variance. I'll tell you what that means and the assumptions necessary for one-way analysis of variance, and use it to carry out hypothesis test against a mean that several means, or a null hypothesis that several population means are equal. I'll show you some actual analysis of variance tables from SPSS, and we'll go through those, and I'll show you how to interpret them, and carry out post hoc tests for following up an analysis of variance. And this is the appropriate chapter in your text is 5.5 from Open Intro. Recall the cell phone study from last class when we were doing the independent samples t-test. So not the one where they were paired, but where they were unpaired. And you'll recall that in this study, we had two groups. We had a control group, which had no cell phone, and then a comparison group where people were talking on a cell phone. And so they're different people, they're independent samples, and we wanted to compare the mean response time to a stimulus, such as something running out on the road in front of them in a simulated driving environment. And here the null hypothesis was that the mean response times of these two groups were equal, and the alternative hypothesis was just that they were not equal. And we used an independent samples t-test to do that. We used a t-test because we had to estimate the standard deviations from the samples, and there were small samples, right? If we had somehow known the standard deviations, we could have used a z-test, but because we estimated the standard deviations, we used the t-test. I know it's hot in here, isn't it? I'm sorry, I feel it too. It's even warmer up here where I am. Maybe next class I'll wear my swimming trunks. If you can't go on vacation, you might as well sit in a hot room, right? Okay, so let's imagine another study where instead of just two groups, cell phone or no cell phone, this is a more modern study where one group has voice available, they talk on the phone, and the other one has voice and data, so they're receiving a stream of text messages along the way. And there are now potentially three different means. There's the mean response time for people with no cell phone, mean response time for people who have an old-fashioned cell phone that only gets voice, and another group that gets voice and text messages and Facebook updates and whatever else on their cell phone. So there are three different groups, and this is where we will bring in analysis of variance. Here's another example, an evaluation of training programs. Doesn't matter what it is. The important parts for applicability of analysis of variance is that we have a continuous outcome. So here, instead of response time, it's a learning time using 3 different training methods. And these are learning times, let's say in minutes, of 3 individuals by 3 different methods. So those are our data. And we're going to test a null hypothesis that these 3 training methods are the same. Here's some descriptive statistics. The first thing that you're going to do when you test hypotheses, and we're seeing here, so for each of these groups, there's just 3 observations, and we see the means and the standard deviations. Means are 12, 10, and 22. And the question here really is, are the difference in means more than you would expect if the population means are the same? Because even if you have the same population means for these 3 methods, so maybe they're all really the same method, you're going to get some variation in your sample means, right? Just due to sampling variation. Looking at these 3, I might guess that, just off the top of my head, that means of 12 and 10, that's not too big of a difference given that the standard deviations of these are 3 and 4, more or less, right? So maybe that difference in means, I would guess, is consistent just with individual random sampling variation, even if the population means here are the same. This, on the other hand, so a mean of 22 and a standard deviation of 4, that's looking like a kind of a big difference in means. So just qualitatively looking at this, that is like your in the mind analysis of variance. You're saying, is the variability in your means consistent with the variability of the individuals? Does that make sense? And if your variability in the means is quite big compared to the variability in individuals, then we're probably going to reject the null hypothesis. And that is analysis of variance in a nutshell. That is all it is. And in fact, I'm going to show you an F statistic later today. An F statistic is literally that. It is the variation in the group means divided by the variation within the groups. That is what the analysis of variance will be based on. Yes?
Professor, go back to that point where you said, rejecting a null hypothesis, and the variability of means is greater than, so it always has to be compared to the standard deviation. You say the standard deviation is this amount. Whoa, the mean is this much more.
Yeah, that's right. So it's a comparison. It's a comparison of the variability between the groups to the variability within the groups. If your variability between groups is large and within groups is small, you're going to reject the null hypothesis. But if they're comparable, like your variability between groups is about the same as your variability within groups, then you're not going to reject the null hypothesis. But you have to have that basis of comparison. We can't say whether the difference between 10 and 22 is big if we don't know what the variability of individuals is. Good question. So here's a box plot of that example, showing, this is kind of a silly case to show a box plot since there are only 3 observations. I actually would recommend probably that you show a dot plot here and just show all of the observations, because you're just hiding the fact that there are only 3 data points in each of these by showing a box plot. Not a very good choice of descriptive statistics, but there it is. You still can see kind of the variability within groups and the variability between groups, and you see that there is kind of a big difference in method 3. So again, just looking qualitatively, making a guess. I'm going to guess that we're going to reject the null hypothesis just because the difference in method 3 is too big to be consistent with the individual variations. So you could use t-tests, right? We've got 3 methods. You could compare method 1 versus 2, 1 versus 3, and 2 versus 3. You could just compare pairs of groups and see if any of them are different. You would have to keep in mind as you do that, that if you're using an alpha of 0.05, then in each of those tests, you've got a 5% chance of type 1 error. And so if you keep on doing it, your chances of making one type 1 error are going to increase. Right? By the time you do 3, your chances of making one type 1 error is going to be something greater. We could calculate it even using stuff that you learned in lecture 2 or 3. But it's not hard to believe that suppose we had 6 groups, then there are a lot of pairs, and your type 1 error is going to get higher and higher. It is possible to control for type 1 error. So, you can make a correction to your p-values. There are methods like the Bonferroni method, which I'll show you later, but it's not as powerful as doing a single test with the analysis of variance to see if there's just one test to say, is there any difference anywhere that's inconsistent with individual sampling variation. So, so instead of doing all of these pairwise comparisons, we're just going to do one test. Oops, sorry. So here I actually calculated what that type 1 error probability would be if we have 3 groups. So the probability of not making a type 1 error on one of them is 0.95 cubed 1 minus that. Our type 1 error rate is actually up to 14%. And again, that's not the end of the world. You can do corrections that help with that multiple testing problem, but it's not as good as doing an analysis of variance. So here's another picture of this basic idea of ANOVA. On the left here, we've got some difference between the groups, but a fairly big difference within the groups. And that difference within the groups kind of obscures the differences between the groups. And it makes you think that maybe these differences in means between the group are just random. Whereas on the right here, these are the same means of each group, but the within group variability is less. So the one on the right is less likely to have happened by chance, those difference in means. This is just another view of those 3 groups, say those 3 methods, but looking at the population, probability distributions, where we have 2 populations where the mean is fairly close, and there is variability within each population that is fairly large, and then a third where that difference in population is fairly large to the within groups. So this would be a case where actually all 3 of the populations are different, but you would just need a larger sample size with differences like you see on the left than you need with this difference that you see on the right. So our population parameters, we're going to have a mean and a standard deviation. That's because we're assuming that these are continuous variables and they're normally distributed. So we completely describe the variability in the population with a normal distribution with several means, a mean for each of the groups and a standard deviation for each of the groups. And I lost the, I lost something here, but this should have been x bar 1, x bar 2, up to x bar, the number of groups that we have. So the population parameters are the ones that we don't have access to, but we assume that there is some true value of, and the sample statistics are what we actually observe. And we have a mean and a standard deviation for each of our several groups. So recall, let's compare these hypothesis tests. We started with one population, and we just compared a null hypothesis that our mean of interest was equal to a theoretical specified value, so some fixed value of the mean that we either knew a priori for the population or was some number of interest based on a regulation, something like that. But we're only taking one sample and comparing that sample to a population mean. Then we did the two sample t-tests and z-tests where we compared two means. So we estimated the mean and the standard deviation for two different samples. We did that with the t-test. And by the way, you could do that with the ANOVA. They are equivalent. So you'll get the same p-value whether you use a two-sample t-test or a one-way ANOVA in this case. But once we have multiple populations, so we have three or more means, we have to use ANOVA. And the null hypothesis is going to be that all of those means are identical. And the alternative hypothesis is that they are not identical. So if we reject the null, it's not going to tell us where the difference lies. It'll just mean that there's evidence that these means are not identical. And so we have some assumptions about this. By the way, anyone who can tell me, let's see, tell me, I'm going to go on to the next page, how the null hypothesis is different for the one-way analysis of variance than for the t-test. And I would offer you a margarita or something in here, but I don't have that. So how about give me one more example of a case where we can use a one-way analysis of variance that we haven't covered. An example, an example that would meet the couple requirements that we've gone through so far for using an analysis of variance. Yep.
You said, actually no, it was going to be to reject it or accept it. I was going to say the reason to accept or reject it. That's not the reason for using it.
Yeah, I want an example, like a real life example where you might use an analysis of variance, and then give me an example and I'll talk about why it is or is not appropriate for an analysis of variance. Mm. Smoking and age impacting on stenosis. So that's a tricky one because you then have two different independent variables. So the example was, instead of just the impact of smoking on stenosis, the impact of smoking and age on stenosis. Yes, you could use an analysis of variance, but it would no longer be a one-way analysis of variance because you have two different independent variables. That would actually be what we call an analysis of covariance, when you have a mixture of continuous and categorical variables as your predictors and a continuous outcome. I forget, what are the units of stenosis? Let's say it's a continuous value. It's like a something that varies continuously. It's not just a yes, no, right? Okay, so in that case, you're not going to do an analysis of variance at all because your response variable is not continuous. You can't calculate the variance. Yeah, blood pressure. So, so if you had age and smoking, yes or no, as independent variables, and blood pressure as your dependent variables, that would actually be an analysis of covariance. But you would read your ANOVA table similarly to what we're doing today. And an example of a one-way analysis of variance would be if instead of just smoking yes or no, you had non-smoker, smoker of cigarettes, smoker of e-cigarettes, smoker of hookah, and your response or your outcome variable is blood pressure. Then we would use what we're using today. Mm-hmm.
So, for example, for the project that I'm working with the hepatitis C support group, so there's a control group where we were trying to look at if attendance of hepatitis C groups impacts knowledge of and attitudes and beliefs regarding hepatitis C. So
I'm going to try something, since actually, because I can do this now, I'm going to just come down here so that people online can hear you.
So the control group is individuals that, control group are the individuals that didn't receive the hepatitis C support and education groups, so that they didn't receive the intervention. Then in the intervention, we had the individuals that did receive the intervention and that attended at least one support group.
Yeah.
And then, but there were individuals in the intervention group that didn't attend no groups. So there's three different groups.
Okay, so you have a control group that's no intervention, then you
Right.
have an intervention group with support groups and without support groups.
Right.
Yes, that could be a one-way analysis of variance. What's your outcome variable?
Hepatitis C knowledge, attitudes, and beliefs. No, that's not the variable.
Depends on what your outcome variable is and whether it's continuous or
Like a
categorical.
score on a post-test.
Yeah.
Okay.
If it's a score or something like that,
Mhm.
you could use an analysis of variance. If it were just like, you know, a yes or no belief or something like that, then it would be like a chi-squared test.
Okay. So then we will use the scores of knowledge, attitudes, and beliefs from the pre and post.
Right.
Okay.
Pre and post, you mean pre being the control and post being the...
Well, we did pre and post for both the control group and the intervention group to see if the intervention had any effect on the pre and post.
Improvement.
Right.
Yeah, so
That
it's
would be the
so tricky design. So it's a paired design because you have pre and post measurements. So you could take those differences, if it is a continuous score, and then do an analysis of variance on the differences.
Okay.
So it's an analysis of variance as long as you have 3 or more different groups and you have a continuous outcome variable. Good example.
It's a tricky study.
It sounds like it. Thank you. All right, I see we do have 10 viewers online, but but you're all quiet. Feel
I don't know if it makes a difference. I was downstairs with Tony and he wasn't like seeing anything. Did we ever get confirmation that this is like working?
you're watching through the online
Yeah. So then, yeah.
hangout on air, so I think so. That's what I like about this setup. I'm actually broadcasting it from my laptop, but then just tuning in from the desktop to show there. So I don't think there can be anything wrong. Okay. So the first assumption of analysis of variance is that either the data are normally distributed or the sample size is large. And I mean normally distributed within the groups. So it's possible to have groups with a very different mean, where if you just put all of your data together, it wouldn't be normally distributed because you have this big difference in means. But what I mean is that if you were to subtract the means of each group, what you would have left over would be normally distributed. Now, ANOVA is extremely robust to violations of the assumption of normality. And it's also conservative, meaning that if the normal assumption is violated, your p-values tend to get larger. So you're not going to reject your null hypothesis incorrectly. If anything, you'll lose power, meaning that you will fail to reject the null when there is some difference. But that is going to be a problem mainly if you have some extremely skewed distribution or big outliers and a small sample size. One thing that some people do is there are tests of normality, and some people will actually test the normality assumption. I don't recommend that. I remember the intro stat textbook that I used long ago. They likened that to, I think they called it sending like a little rowing skiff out on the ocean to see if it was calm enough for an ocean liner. So you have some test that is very sensitive to departures in normality, and the bigger your sample size, the more powerful it is to detect departures in normality, but the less that matters for ANOVA. So you're sending out a little rowing skiff onto the ocean and it tips over and you tell your ocean liner that you can't use it today because it's too rough. Does that make sense? So, yes, question.
Yeah, when you say data are symmetric, is that measured normality?
Yeah, so what I do recommend is just plotting your data and seeing, does it look really non-normal? So if it looks kind of symmetric, doesn't have huge outliers, then you can use ANOVA even if your total sample size is less than 15. If your sample size is up to 40, then even with some skew and a few outliers, ANOVA is still fine. And as your total sample size is greater than 40, then even skewed data with outliers is probably fine. There are so-called non-parametric alternatives to one-way analysis of variance if the distributional assumptions, so the assumption of normality, is not met. But I wouldn't resort to them unless you look at your residuals plot and decide based on this that you have a small sample size and some really obvious departure from normality. It's a judgment call though. But remember that if you get a p-value from your ANOVA and it's under 0.05, you can be pretty confident that there is a difference because it's conservative. Does everyone understand what I mean by conservative now? All right. The second assumption we call homoscedasticity. That means that the variance of each of the groups is equal. And again, there are tests of homoscedasticity like there are tests of normality, and I don't recommend them for the same reason. They're too sensitive, they're not really relevant. But you can just look at the standard deviations, you can calculate them, and if there are no differences greater than 2, then again, it's not a big deal. If they are extremely different, then you might need a different method, again, a non-parametric method. But again, the test is conservative when this is violated. So it's a very safe test to do. It's a nice property. And of course, randomization. We always assume that. So prerequisite for every test we do, that the subjects end up in the groups randomly. Here's how you do an ANOVA. So you need 2 calculations, and we looked at them visually before. There's a variance within groups and the variance between groups. So let's look at the variance within groups calculation. S1, S2, these are just the standard deviations estimated for each of the groups. So with those 3 methods, I showed you the standard deviation calculated for each method, and then they're weighted by the sample size of that group. So if you have a large group and some smaller groups, then that large group counts more towards your overall estimate of the within group standard deviation. Makes sense, right? It's just you have a better estimate of the standard deviation from that large group, so you do a weighted average instead of just a plain average. If you have the same sample size in each group, then it doesn't matter. It's just an ordinary average of all of your variances. The denominator is not quite just your total sample sizes. It's your sample sizes minus the number of groups. And that is what we call your within group number of degrees of freedom. You'll recall that when you learned the t-test, the degrees of freedom mattered, right? You had to calculate a degrees of freedom that was your sample size minus 1. It was a little different for when there were 2 samples, but there was a different t-distribution for every number of degrees of freedom. ANOVA is a little bit more complicated in that there are 2 degrees of freedom, and the F statistic, which we're going to use, has a different distribution depending on both of those degrees of freedom. So we don't actually even use the table of F statistics because it would need to be so big, because you need to have the value, your set of values for every pair of degrees of freedom. But it's still good to know how to calculate them, because they'll help tell you when you read your analysis of variance output that you did everything right. You should be able to do on a piece of paper, calculate your number of degrees of freedom and make sure that that's right in your output. Good way to avoid making errors. So that's the within group standard deviation. It's just a weighted average of the standard deviations of the individuals in each group. And then there is the between group standard deviation. And all this is the variance of the means themselves. So recall back here, we have a mean for each of these groups. It's basically, if you considered these to be 3 data points and calculated the standard deviation and the variance, that's what the between group variance is. So looking graphically on here, or let's say looking graphically on here, the within group variance would be, since it's the same all here, for all of these, it would just be the variance of this normal distribution. The between group variance would be if you take these three means and calculate the variance of those. So it would be, you would take the average of all three of them, which would be somewhere about here, and for each one it would be the sum of, the squares of the differences of that mean to the grand mean. So the mean of all of these three means. Good and confused now? No? Good. But it's still, don't let the formulas confuse you. The idea is simple. You know, there's variability within the groups and there's variability between the groups. And you calculate those two variances. These are the formulas for calculating those two variances, and the denominator is the number of degrees of freedom for each of those variances. For within, it was the total sample size minus the number of groups, and for the between variance, it's the number of groups minus 1. Yes?
And so you would use this just because the T tests aren't good enough? Like this is better for what reason?
Because the t-tests are just for 2 means. So I would use this if there are 3 means, if there are 10 means. You don't really, if you have 10 groups, imagine you don't really want to go and do, I think it's 10 times 9 over 2, 45 t-tests, right? You can just do one analysis of variance and find out if there's a difference somewhere in those. Yep.
Question those groups that they gave us in that, let's say, I'm doing the flu shot of 2013 data. We're specifically comparing 2 groups, then we can say we just, even though there was X amount of data, we chose to compare 2, and then we could use that chi-square for that case. Depends how far we want to expand it to, right?
So
Like in our project, we compare
Yeah.
so many combinations.
you compare combinations, but is there a continuous variable?
There's one set of most of them are nominal.
Yeah, most of them are nominal, so you're going to use like a chi-squared test. Yeah. If you have 2 variables, one of them is nominal and one of them is continuous, then you can use ANOVA. Did you have a question? Okay. Right. Flu shot as outcome is yes or no. Yeah. So the total variability then is the sum of these 2 things. It's the sum of the between groups variability and the within groups variability. And in your ANOVA table, you'll actually see it broken up that way, and you'll see a total, and you'll see that when you add these 2 things up, it adds up to your total. Which actually is kind of neat, and it's not totally obvious that if you were to just calculate your variance of all your data points independently of the groups, the variance you get is equal to the sum of these 2. That's neat, right? I don't know, I find it surprising, but you use those two things, the between and the within group variances, to calculate your F statistic. And who would have known that a statistic this simple, it's just the direct ratio of these 2. Like, I can't imagine a simpler summary of the between group to the within group variance. It's like the simplest summary you could possibly think of, and it turns out to be the most useful one too. That's the F statistic, right? It's just the ratio of those 2. So if you have a big difference between and a small difference within the group, you have a big F statistic. Yes?
So when are you using variance, variability, and standard deviation?
I'm using them interchangeably. Like, I mean, variability is this, or variance is the square of the standard deviation. But I'm sometimes just saying variability because it's a more common English word. But I'm using variance as a description of variability. You know, there are other descriptions of variability, but we're going to use variance.
But so S squared.
So S squared is the variance, where S is the standard deviation. Yeah. So yes, in this formula, S is the between sample standard deviation estimated from the samples, and S within is the within sample standard deviation. You square those standard deviations, take the ratio, that's your F statistic. Here are some examples of what the F distribution looks like. And as I mentioned, it has two different degrees of freedom. It's got numerator degrees of freedom, it's sometimes called, which is the between groups, and it's got denominator degrees of freedom, which is the within groups, right? Does that make perfect sense now, that your numerator is the differences between the groups and your denominator is the differences within the groups? So that when you have big differences between the groups, you get a big F statistic. And that F statistic depends on your number of degrees of freedom in each. So let's see, let's look at some of these. So if we have the black here is one numerator degree of freedom and one denominator degree of freedom. And in that case, we get a pretty long tail, and we have it centered somewhere down here, close to 0. Now, the reason is that when you have very few samples within each group, it's hard to have a large within group. Your within group variability is going to tend to be large compared to your between group variability. When we have big samples, so we have 100 and 100, so these, remember the F statistic, the F distribution is going to be when the null hypothesis is true. So this is the distribution. If you keep on taking samples with 100 numerator degrees of freedom and 100 denominator degrees of freedom, this is the distribution of F statistics that you're going to get. And with a fairly large sample size, that ratio is going to be around 1. Same variability within and between groups. Now, here's something that's a little different about the F distribution compared to the T and the Z, but similar to the chi-square. Where do you think you're going to reject the null hypothesis if you calculate your F statistic and put it on this distribution? Let's take the gray one, the 100 and 100. So we tend to reject the null hypothesis if our test statistic is far in the extreme of the tails of the null distribution. And so we could get something up in this right tail, or we could get something over in this left tail. Where are you gonna, in which case are you gonna reject your null hypothesis? Or both? Right tail. Why the right tail? Gut instinct, okay, fair enough.
I think that's like very large compared to the left tail.
It is very large compared to the left tail. Yep. Any other guesses and explanations why? So here we could have an F statistic of say 0.001. That's going to be in a very low probability region of the tail, or an F statistic of 5. Are we going to reject the null in both of those cases, or just one of them? We have one vote for the right tail. Anyone want to agree or disagree? How would you interpret that? So let's say we have an F statistic of 5. What does that mean? We're calling our calculation here. What does an F statistic of 5 mean? Mm-hmm. Right. Right. Which sounds like the case when we want to reject the null hypothesis, right? The other way. Yeah, if F is 5, that means that there's more variability between the groups than within the groups. If F is 0.01, then that means that you have much bigger variability within the groups than between. And that's kind of weird. Like, why would that happen? That would mean, like, say we're looking at blood pressure, there's, a fair bit of variability in the population, but in all of your different groups, they have exactly the same mean. That's weird, right? You don't expect that to happen. In fact, one case that can happen is if there's been scientific fraud. Someone has cooked their data and added more data points to make the group means very close to support some hypothesis. Yes. Yes. So we have several groups, such as non-smoking, smoking cigarettes, and smoking e-cigarettes, and smoking hookah. The null hypothesis, and we want to know how those might influence on blood pressure. The null hypothesis is that the blood pressure of those 4 groups is the same. And the alternative hypothesis is that at least one of those groups has a different blood pressure. Average blood pressure. Right. Exactly. So if smoking raises your blood pressure a lot, then it means there's going to be more of a difference in means, more of a between group variability caused by that difference in means, and it makes you more likely to reject your null hypothesis. So even though the analysis of variance, it's inherently a two-sided type of test in that it doesn't matter if one of your means is greater than or less than the other means, but it's just we only use the right tail of the F distribution. So it's like the chi-square test in that way, that you just calculate the probability under the right-hand tail. And as usual, we're going to reject H0 if we get a probability under that right tail that is less than alpha. So going back to those 3 training programs and drawing it out here, so the 3 data points with a line in the middle, and this middle line showing where the mean within each of the groups is, and a horizontal line showing where the grand mean is. Our standard deviations are calculated within each of these groups. our between groups mean is calculated by these red arrows, so the differences of each mean from the grand mean. Here's what you get if you actually plug it into SPSS. It's going to give you this ANOVA table. So this ANOVA table actually says there's between groups. So sum of squares, that's actually, so the between group sum of squares is going to be the differences of the mean of each group from the grand mean. So it'll be these red distances squared and added up. The degrees of freedom for the denominator, remember, is just the number of groups minus 1. So we had 3 different groups. Degrees of freedom is 2. And one good reason that it's good to calculate your degrees of freedom in your head and check is that a very common mistake here would be if you were using a numeric indicator for your groups, like 1, 2, and 3, and you accidentally did your analysis of variance using it as a numeric variable, then you're going to get a degrees of freedom of 1 here, and your result is going to be wrong. But if you checked and said my degrees of freedom should be 3 minus 1 is 2, then you would know that if degrees of freedom is anything other than 2, then your output's just wrong. You need to go back to your data and fix that and run the analysis again. So within groups, remember we had 3 in each group. So that's a total of 9. So we have 9 data points minus 3 groups, so that's 6 degrees of freedom. Our mean squares, it's the sum of squares divided by the degrees of freedom. So that's part of why degrees of freedom matters, because it goes into your mean square, which is your variance. Now F should just be the ratio of these two. I don't have a calculator handy, but if you go 124 divided by 11, you should get 11.273. And then SPSS calculates the probability under the right tail of the F distribution with 2 and 6 degrees of freedom, gives you this p-value of 0.09. And back as we kind of guessed from the plot, this is a significant difference in the means. Yep, so that your p-value is less than 0.05, we're going to reject the null hypothesis. So coincides well with what we saw in the plot. You know that this group here looked kind of inconsistent with the other two. This difference in means looks like too much compared to the variability that we see within the group, and indeed the statistical test tells us that these didn't come from one single mean. The null hypothesis would be, that they're all the same mean, and it would be about 15. 15 would be an estimate from the sample, but the rejecting the null means that these 3 groups probably did not all come from this one mean. So F statistic, p-value, there's your hypothesis test. So because we reject the null hypothesis, we're going to say at least one of those training methods probably results in a different learning time. But the ANOVA doesn't tell us anything about which. It just says there's a difference somewhere. From there, you can look at a plot like that and say that it's probably method 3. But you can also do post hoc tests, which is something you can get from SPSS or other software that will actually make all of those pairwise comparisons and make another nice plot for you to show you where the differences are likely to lie. But we only do that if the F-test is significant. So because we rejected the null hypothesis, we can go ahead and do the post hoc tests if we do not reject the null, then we do not go ahead and do the post hoc test because we don't believe that there is any difference. Here are a few options that you'll have, and it really depends on what your study design is and what kind of tests you want to do. The Bonferroni method is a very generic method that you can, as long as you plan some number of contrasts, either all of them or just some of them, you can use the Bonferroni method to correct for multiple testing. Do you remember the multiple testing problem I showed you earlier? If you were doing 3 comparisons, the problem was that your chances of having at least one type 1 error, even with alpha equals 0.05, becomes greater than 0.05. And these methods will help you solve that problem. And what they will do is alter your p-values. The Bonferroni method is actually very simple. If you do 3 tests, all it does is multiply each of your p-values by 3. So it means that your p-value, in order for that comparison to be significant, is going to have to be less than 0.05 over 3. That's all the Bonferroni correction is. There are some other methods. This Tucky method, which I think is the default in SPSS, because it is good for doing all pairwise comparisons in a group. There are some other ones, this Dunnett method, if instead of doing all pairwise comparisons, you have a control and you want to compare several treatments to it. So in that example of non-smoking, smoking cigarettes, smoking e-cigarettes, smoking hookah, you might use the Dunnett method just to compare the 3 different methods of smoking to non-smokers. Or this Sue method, I don't think you're going to use that, but if you just wanted to take your best or your most extreme mean and compare everything to that, you could use this method. The Tucky method or any of these, you can get corrected confidence intervals for them and use those to decide which of the pairwise comparisons are significant, in the same way that you've used confidence intervals for hypothesis tests before, that if that confidence interval on the difference of means doesn't cross 0, then you say there's a difference between those 2 means. So here's an example of the Tucky honest significant difference method from those 3 learning methods. You get a difference in means for each one. So method 1 compared to method 2, the difference in means is 2, and compared to method 3, the difference in means is -10. Then a standard error, a p-value, and a confidence interval. So remember, between method 1 and method 3, there was a big difference, and this confidence interval doesn't include 0, and the p-value is less than 0.05. So we would say there's probably a difference between method 1 and method 3. There's also probably a difference between 2 and 3, and then this is just a repetition, 3 and 1, 3 and 2. But where there is not a difference is between method 2 and method 1. Yes? Yeah, so these confidence intervals are intervals on the difference in group means. So this is the lower bound of your 95% confidence interval on the difference in the mean learning time for people who got learning method 1 compared to people who got learning method 2. So you're saying that you're 95% confident that the difference in the learning time for these 2 groups is between -6 and 10. And because that interval includes no difference between the group, you're not gonna, you're not that confident that there is no difference between the groups. Right. And this output will give you those pairwise comparisons for all the pairs. So for 3 means you have 3 comparisons, 6 here because it has repetition, because it's giving you 1 versus 2 and 2 versus 1 as well. Yes.
I was just gonna say, can you repeat how we can tell based off this chart that there's no difference between 1 and 2?
Yes, I can. So when I look at this chart, I want to know where the difference is. Here was the graph. Based on the graph, I thought probably there's a difference between 1 and 3 and between 2 and 3. Or looking back at, where was the plot at the beginning? Here, you know, there's not much difference between 1 and 2, but there is a difference between 1 and 3 and between 2 and 3. So we've done the ANOVA. With the ANOVA, we got a p-value less than 0.05. So we think there's a difference somewhere. And then we do this Tucky HSD method. It gives us an output like this. Tells us what the difference in means is. And then there are 2 ways from here that you could decide which of these are a real difference. The first is from these significance values, these p-values. You could just look at all the ones where it's less than 0.05 and say we have strong evidence of a difference for those. So between 1 and 3 and between 2 and 3. Whereas between 1 and 2, we have a p-value of 0.71. It's not less than 0.05. So we don't think there's a difference between 1 and 2. Alternatively, the other way is with the confidence intervals. These are confidence intervals on the difference in means. So the difference in means between 1 and 2 is 2, and then the margin of error is about 8, or about 8.3. So the upper bound on the confidence interval is 2 plus 8.3 is 10.3, and the lower bound is 2 minus 8.3 is minus 6.3. So everywhere that the confidence interval includes 0, there might not be a difference. But if that confidence interval does not include 0, like in the second row, then we think that this difference in means that we observed is not consistent with the null hypothesis. Now keep in mind that it's possible that you can get ANOVA is a very powerful test, meaning it has good power to detect a difference in means, and it has better power than just doing Tucky HSD. So it's possible that you can have, instead of something like this, maybe you just have one mean here, one here, and then one here. And so in that case, then maybe the difference between these 2 would be different. But maybe if the first one was, I don't know, just like this or something. So none of the individual pairwise differences are that big. You could have a case where your Tucky's on a significance difference. You don't see any significant p-values, but in your ANOVA you do. And the reason that can happen is that you have maybe several differences between your means that are more than you would expect by chance, but none of those pairs are very extreme. So just because you don't reject anything in Tucky's method doesn't mean there is no difference in means. It's also nice to get, and I think there's a way to do this in SPSS to actually plot the confidence intervals from the Tucky method. So these, oops. So if you did that, then it becomes very obvious which ones you can clearly reject, because you have this 0 line, all of the confidence intervals that intersect with your 0, you would not reject, and the ones that don't cross, you reject. Looks like my numbers down here got a little bit off. This 0 should be under that line, but you know what I mean. All right, so time to wrap up. We use the F-test to test the null hypothesis that 3 or more means are not identical, or the null hypothesis that that several groups have the same mean. And like the chi-square test, the chi-square distribution, we use just the right tail of the F distribution, even though it is inherently a two-sided test. We have these assumptions: normally distributed population, homoscedasticity. Sorry, heteroscedasticity would be the violation. I'm going to write that here. A little hard to write, but homoscedasticity and independent samples. And you use those post hoc tests only if your analysis of variance gives you a significant p-value. Any questions? Otherwise, we can go down to lab. I'm going to stick around. I'll be happy to talk about projects with any of you. And I'm going to, if no one, I'll still be down there. I'll use the time to catch up on all of the emails that came today. There's tons of emails about projects. I feel your pain. Okay, thank you.